It's my pleasure to introduce our first organizer, Professor Shane Snyder. Professor Snyder is the José Domingo Pérez Foundation Chair and Professor at Georgia Tech. He's a renowned expert in water quality, treatment, and sustainability with over 300 publications and too many citations to count here. Recognized as a top global water researcher and ranked among leading environmental engineers by Stanford University, he also serves as editor-in-chief of Environmental Science and Technology, Water, and previously of Chemosphere from Elsevier. A fellow of the International Water Association and a board-certified environmental scientist, Professor Snyder also continues to advise global organizations, including the EPA and the WHO. And as you can see, he's very well positioned to lead our first panel on desalination and membrane processes. So with that, I'd love to turn it over to you, Shane, and we look forward to an exciting panel.
Okay. So first and foremost, I'd like to thank the ACS for putting this together. It's certainly an important topic around the world, and I'm honored to be part of that. So can I have my first slide, please? Maybe the next one. Great. So I noticed that, our session is both desalination, which is largely membrane, not all, but also membranes for clean water in general, which is more of a filtration membrane from my experience, and I'm not a membrane expert. But it's interesting to think back that actually the concepts of filtering water runs thousands of years ago. Early artifacts suggest clay pots that were used to filter water. Perhaps the most well-known in history was the Hippocrates water sleeve, which was cloth, used for filtering water, also for wine, and the idea to remove particles that would give off taste. And later, particularly with John Snow's epidemiological discovery of cholera being spread through water, that filtration could remove pathogens and reduce disease and death. The ability for osmotic phenomenon was discovered first in animals. Actually, if we think about our kidneys or other membranes in the body that are well positioned to do filtration, to allow certain materials to pass and others to be rejected. So today, as you're going to hear, membranes are widely used around the world. We'll hear from three very well-known experts in the field. And coming back to the Sustainable Development Goal, specifically for water, by 2030, we're to have universal and equitable access to safe and affordable drinking water for all. And membranes will certainly play a part in achieving that goal. Next slide. So just a tiny history. I found it interesting that in 1922, Richard Zimandi from Göttingen actually was awarded a patent in the United States for a microfiltration membrane. Now, this is far different than what we had today. But Zimandi went on to win the Nobel Prize in 1925 for his work on colloidal materials, which became a form of microscopy that he developed, which is able to characterize particles, or today we can think of this maybe as turbidity. Next slide. So I got involved in membrane technology, not as an expert, but more of an applied side when I was working for the city of Las Vegas back in the late 1990s and early 2000s, where first we had a very unfortunate or tragic cryptosporidium outbreak, which resulted in deaths in the city and a lot of illness. And then in the early 2000s, partially related to climate change and drought, we had an epic eutrophication of Lake Mead, which also clogged the conventional filtration systems and made us look into the potential for large-scale membrane technology. Next slide. And today, we continue that journey. Again, you'll hear from some great experts. I just came back from living 7 years in Singapore, working at NTU University in Singapore. And Singapore adopted the largest ceramic membrane system in the world. And so looking for more resiliency and life cycle assessment. And we published recently in ES&T Waterways to optimize those types of processes, which I think you'll hear more about. Next slide. So just again, a little history on desalination membranes. So a different type of membrane, obviously. Some of the earliest work from the late 1950s from University of Florida showing a thin film desalination membrane. Next slide. And also, and Eric Hoek must be proud, UCLA publishing in 1963 in the American Chemical Society Journal, Advances in Chemistry, again demonstrating the potential for a thin film membrane to be used to produce fresh water from seawater. Next slide. So around the world, we have large populations along the coast. You can see literally around most parts of the world, the coastline has various size communities. Next slide. So about a third of the world's population live within about 100 kilometers of the sea, and those populations are often twice the density of the global average. Next slide. And I'm looking forward to hearing our panelists speak about this. According to the International Water Association, an advanced water treatment facility might be at, say, 1 kilowatt hour per cubic meter, whereas state-of-the-art desal plants are somewhere around 3. I know there are some that are lower, but still around 3 times the energy requirement of a typical advanced treatment facility. And remember that 2/3 of our population don't live near the coast, so a lot of people might be challenged to use ocean desal. And with inland cities, we have to think about the water that would be lost to the brine during membrane processes, and also where would we put the brine in an inland city. Next slide. So again, from where I just came from, living 7 years in Singapore, I just thought it's interesting to look at what they are predicting, and they're seeing growth in new water, which is recycled water, moving from about 30% today up to 55% of their portfolio by 2060, whereas desal is currently at 25%, may move to 30%, and they don't see further growth. So we're talk today a bit more about this, and I will stop there and turn it over to our experts. Let's get our 3. So we're very fortunate to have David Warsinger from Purdue University. He's an assistant professor of mechanical engineering. Eric Hoek, professor in civil environmental engineering at UCLA, also a faculty scientist at Lawrence Berkeley National Labs. And Amy Childress, a dean's professor in civil environmental engineering at the University of Southern California. So honored to give that opening, and I'll turn it over to David.
Thanks very much. So today I'm going to give a brief technology background of desalination, including thermal technologies, and also going over some of the ways we can further enhance the efficiency of the state-of-the-art. So can you go to my second slide? So the leading technology is reverse osmosis, which is one we know well. It's the membrane-driven technology. Also in high use are thermal technologies, including multi-stage flash, multi-effect distillation, as well as electrodialysis, and there's some emerging thermal technologies as well. Next slide, please. So going through these in order, our oldest way to desalinate is simply a solar evaporation. We can think of using solar ponds. This is how the Romans acquired salt, and we still get more than half our salt today from just large solar evaporation ponds. And we can use this for staging crystallization to recover desirable elements, and notably, for instance, lithium, when it's harvested from brines, is recovered in solar evaporation ponds. And there's a lot of research to implement absorbing materials in conjunction with solar evaporation, although implementing those in industry is still needs work. Our second oldest technology are solar stills. You can think of these as clear shoeboxes where sunlight comes in, causes water to evaporate, and that water will then condense on the cooler sides. And it can be multi-stage for improved efficiency. There's evidence of such systems going back to the 1500s, but they're still somewhat less efficient than other technologies. Next up, membrane distillation. I'm still going through these. Membrane distillation, see here, is an emerging technology. It essentially resembles a counterflow balanced heat exchanger with water being preheated on the right side, going through a top heating, and then going down and then it crosses the membrane and evaporates and recondenses. By having it as a heat exchanger design, you can get good thermal performance and good inherent energy recovery while having one very simple device. You can see here the key on the right. To unify these processes, we have a systematic color code. Pure waters is aqua color. In a blue-gray, we have water vapor. I've shown with arrows where the water vapor is flowing. And I have a color code here where blue is cooler, red is warmer, and there's an increased density of little dots to convey if the salinity is higher. So next up, multi-stage flash. This process really grew a lot after World War II, and it was the dominant technology before reverse osmosis membranes could really take over. It is called a flashing process because in each stage, water will evaporate from the saline water at the bottom that you see, and then will be condensing on a heat exchanger that is preheating the feed through each step. And you might have 24 of these stages. Multi-stage flash and multi-effect distillation operate in the vapor dome, where we're having an equilibrium of water vapor and liquid water, so that at every single stage there's a different associated pressure and temperature of that stage. And this gives us high heat transfer coefficients and good energy recovery by having many stages. The next technology, multi-effect distillation, has been emerging and in some cases replacing multi-effect multi-stage flashing as a leading technology because of its high efficiency. And this technology similarly has multiple stages. It similarly has preheating of the feed you see at the top here. It does some of the heat recovery and external heat exchangers, which you see on the left of this diagram, but it uses a spray evaporation process onto a heat exchanger that contains vapor from the previous warmer stage. This causes some water to evaporate, the vapor is collected, and water leaving that stage goes through a heat exchanger and is condensed in the subsequent stage. Evaporation gives us really high heat transfer coefficients and thus lower temperature drops and gives us higher performance. And in general, these systems outperform the efficiency of multi-stage flash systems. Finally, shown here, we have humidification dehumidification, which uses spray evaporation onto a packed plastic material. And this causes water to evaporate, the vapor transport over to the right chamber where it is condensed. As a process, this resembles a rain cycle. It is also very amenable to extremely high salinity situations because we can just dispose of a fairly cheap plastic packed material that the water is sprayed onto. And so we can use this for inland water treatment at very high salinities where it has its current niche. Now, next slide. So the leading technology, of course, is reverse osmosis desalination and is leading because of its high efficiency. We talked about membranes. These really operate heavily based off a high pressure pump. So you see here, water comes from the feed, is pressurized above the osmotic pressure, goes through an RO module. Some of it comes out as brine, some of it comes out as permeate. We see here on the right a diagram of the pressure versus the recovery ratio, which in this system, the recovery ratio you can think about as the length along the reverse osmosis module or the RO membrane module chains. And we must apply a pressure in these systems above the final system pressure in order to overcome the membrane permeability and actually have desalination at the end. This leads to a lot of excess pressure, which results in excess energy because the energy is all pumping work, which is PdV work, pressure times volume. So advance, please. One of our major innovations we're working on is batch desalination processes, which instead of applying a pressure that matches the final brine salinity, we follow the osmotic pressure over time in a set batch of fluid and are thus concentrating a batch and then resetting and concentrating again after we flush. This requires a device that can change volume and pressure over time without losses. Here we're showing a reciprocating piston device, and we've had a few different configurations for this. And this also requires a circulation pump, which is shown here. There are other versions that are less efficient, but maybe less complex. So semi-batch RO has no such piston, and that helps us inspire this work. And then pulse flow RO has no recirculation pump. So it's cheaper and maybe can be scaled up to smaller sizes. So next slide, please. So we compared the state of the art, looking at all the desal plants we can find on desal data, and seeing which one had enough information to actually calculate their total energy. There's about 39 different plants together, and we got a sense of the current reported energy demands of seawater desalination facilities, aka SWRO facilities. And this is the current reported here. Then we looked at the state of the art. This includes looking at semi-batch reverse osmosis, or closed circuit desalination as it's called, which I just described. And we looked at the better efficiencies of high pressure pumps, circulation pumps, and pre-treatment and post-treatment technologies that we could use. For our practical minimum estimation, we used our full batch reverse osmosis reciprocating piston approach, and we looked at state-of-the-art theoretical limits on high pumping efficiencies, theoretical improvements on spacer design, extremely highly permeable membranes, and the most efficient pre-treatment and post-treatment choices. And we find, of course, in looking at these, that the biggest potential for efficiency improvements are actually process design changes, such as using semi-batch and batch RO, and not things like more efficient membranes or more permeable membranes, or the pump's already pretty efficient, so you get some more efficiencies there. There are some needs, so circulation pumps for these systems do need efficiency improvements, but high pressure pumps are extremely efficient. Next slide. Sorry, advanced. So here we have, leave these here, diagrams of the least work, the specific energy consumption of these different cases for state-of-the-art practical minimum, thermodynamic minimum as a function of the recovery ratio, your fraction water desalinated, and then our salinity on the x-axis here. And again, 35 grams per liter is our seawater salinity. So we cannot reach the thermodynamic limit, but with the best improvements, including batch RO, we can get pretty close with our practical minimum. Next slide. And so we're working to create a test bed where we compare the best reverse osmosis systems. And so this system that we're building in collaboration with Colorado School of Mines, Zahi Kath, is going to be able to do batch reverse osmosis with a double acting piston, a bladder designed for batch RO, conventional RO, semi-batch RO or closed circuit desalination, and post-flow RO. And so hopefully with system innovations, we can dramatically increase the energy efficiency of these systems and modify these to treat higher salinity situations that today are only done with thermal processes. Thanks very much.
Hi, this is Eric Hoek from UCLA. I can't see my slides. Now I can see my slides. Okay, so Shane asked me to talk about brine management. And so this is the water that doesn't go through the membrane, for example, in an RO system, but the water that remains on the feed side ends up in the form of a sometimes called RO concentrate or brine. So I'm going to start by just defining the problem, talk a little bit about the state of the art, and then talk about some opportunities and things that are happening in terms of innovation for brine management. Next. So as we heard Shane talk about, at the beginning, we have places around the world that are suffering from water scarcity, and this is only going to get worse with climate change, with population growth, etc. Advance, please. If we look into what are our alternative sources of water that we can tap into other than conventional fresh surface and groundwater, you're talking about things that range from stormwater, which is reasonably fresh, municipal wastewater, which is a little bit salty, agricultural drainage waters, which can be brackish groundwaters, which range from on the sort of just above sort of drinking water level to close to seawater. We have seawater and ocean water, and industrial wastes, and other hypersaline waters. The common theme here is that there's going to be salt in any of these alternative waters, in addition to any number of contaminants of inorganic, organic, or biological origins. Advance. So again, as we heard from Shane, the state of the art is reverse osmosis, and also David, sorry. Advance. And one of the key features of RO is that it's a separation process. And so part of the water goes through the RO membrane, and the other part of the water stays on the feed side and becomes a concentrated version of what you fed in. And this pie chart that I'm showing is an example of an inland brackish water desalination application, where if you look at the operating costs, more than half can often be associated with how do we manage this brine, this RO concentrate advance. So the big question, what do we do? Next slide. So the state of the art in brine management ranges from in the lower right, as we heard earlier, salt ponds, evaporation ponds, and then you scrape the salt out and typically dispose of it. It's a waste. All the way on the left, we have deep wells, injection wells, which go far, far underground, thousands of feet, sometimes even thousands of meters, and far below where we get our drinking water from from groundwater sources, into caverns that serve as waste receptacles. In coastal areas, we have, for example, at seawater desalination plants, pipelines which take the brine from the plant and they go offshore a mile or two, and then they disperse it to try to get it to mix quickly with the seawater and minimize environmental impacts. We also have for example, in Southern California, some other places around the world, we have pipelines that go from inland close to 100 miles and all the way out to the coast, which carry all kinds of salty wastes that get treated and then discharged into the ocean as well. And then if someone is required to minimize the volume further, or even to go to zero liquid discharge, in the upper right, I'm showing thermal brine concentrator and crystallizer technologies. These are made of exotic metals because of the high chlorides and the high temperature. These materials have to be highly corrosion resistant. So these are extremely expensive and extremely energy intense, and sort of a last resort only option today. Next slide. So there's a great push to get to membrane-based brine concentration, which would allow us to use lower alloys. We can use a lot of plastic materials and no thermal inputs, and so just running purely electrified brine concentration and crystallization processes. In order to do this, we need some innovation. And so when I think about innovation in terms of membranes, I think on 4 levels: membranes, the modules, the processes. This is a system configuration, kind of like what David was talking about, looking at different process configurations, and in the system itself, the hardware components and how it's actually put together and operated. Next slide. In terms of membranes, what we've seen in the last decade or so, and some newly emerging things, are membranes with very sophisticated surface coatings to resist fouling and scaling, membrane materials that are polymer-like or polymeric, but with ceramic-like properties, which are much lower cost alternatives to ceramics and much higher performing alternatives to traditional polymers. Membranes which are much more robust physically and resist compaction. Membranes which have surface patterns which allow them to create vertical flows and things which resist foulant adhesion. And more recently, even membranes that are electrically conductive and can actively resist fouling and scaling. In the case of scaling, for example, forcing minerals to precipitate in the bulk as opposed to on the surface of the membrane itself. Next slide. In terms of modules, we're seeing a lot of work in the design of feed spacers to promote better mixing, enhancing mass transfer, and minimizing concentration polarization, eliminating stagnation zones and points at which fouling and scaling typically initiate. We're seeing 3D printing and 3D printed spacers on the rise, and they can greatly reduce pressure drop along the length of a system and actually enhance fouling resistance as well. And then other forms of modules which integrate external energy sources like ultrasound vibrations to minimize fouling and scaling as well. Next slide. And then in terms of processes, and I sometimes title this slide something like the land of acronyms, but there are many, many, many acronyms here that relate to different process configurations that get away from the conventional. If you look in the upper left, high recovery processes can operate simply just running RO membranes at higher pressure, or we can operate RO membranes in such a way that we reduce the osmotic pressure drop across the membrane, either by running a saline solution on the permeate side, which is less salty than the feed, but still saltier than typical RO permeate, and that decreases the osmotic pressure drop across the membrane. We can operate with membranes that have lower rejection, and so therefore they have lower osmotic pressure as well. And there's all kinds of complex process flows where you have recycling backward streams and forward streams in different configurations. Ultimately, the goal here is to achieve the ability to concentrate the salt up to about 20 to 25%. Bear in mind, seawater is about 3 to 4%. So we're talking about really high salt concentrations, osmotic pressures in the 200 to 300 bar range, or about 2 to 3,000 psi. And below, we're seeing the emergence of non-thermal membrane-based crystallizer technologies, which can involve a combination of forward osmosis and reverse osmosis membranes. Sorry, back one slide, please. And so we're getting into the range of the ability to both concentrate and crystallize brines into a dry salt or into a salt without adding any thermal energy. So purely membrane-based and purely electrified processes. On the far right, we see a flow schematic. It's too complicated to explain in detail, but this is basically a concept from Saudi Arabia, where they're moving their seawater desalination plants towards zero liquid discharge. And that doesn't mean that they have no liquids leaving the plant. They have fresh water and they have various liquid and solid products that they're extracting. This is called brine valorization or brine mining through the various stages of processes. So they're going beyond just water treatment, and they're trying to harvest valuable materials, things like bromine, lithium, magnesium, and various salt streams, as well as acid, base, and chlorine production right on site at a desalination plant. Next slide. Last, in terms of systems, what we're seeing is housings getting bigger and more complex. You've got things like the barrel from Veolia. You've got this mega vessel that I'm showing on the far upper right, which actually doesn't just combine multiple elements in parallel inside a large 25-inch diameter pressure vessel, but also has bypass flows, which allow you to control concentration polarization, fouling and scaling, and much better, and also to minimize the brine concentration in a way through bypassing the feed flow. And then on the left, a number of attempts have been made around the world at integrating more sophisticated sensing technologies to feed into the automation and control systems to tell you what's happening to the membranes in real time, where it's happening, and what it may be, again, in near to real time. And in the lower right, we're seeing the emergence of a lot of sophisticated machine learning, both physics-based models and statistical models to create digital twins of plants and to come up with more advanced automation and control strategies as we get to these higher performing and more complex systems. Next slide. That's it. Thank you.
All right, thanks, Eric. Okay, I'm going to talk about systems also, but in a little bit of a different sense than Eric talked about them. So here's my system, the coastal water system, where maybe it's the water supply is currently surface and groundwater in parts of California and other parts of the US. We also use imported water. And sorry, my presentation just shrunk. And there we go. Okay, good. And so you might ask, in a coastal scenario, why we're not using desalinated seawater. And that's particularly in California and the US. That's been kind of slow and still is slow in moving towards desalinating seawater. And so the key questions are there energy and environmental impacts, cost impacts. And so next slide. So yes, there are. It's uncontested that desalination is still the highest energy consumption. And it also produces regions of high salinity. When we discharge the higher salinity brine stream, it can sink and sit on the ocean floor where it affects benthic organisms. And also there's impingement and entrainment of marine organisms within on the seawater intake screens and within the intake system. So next slide. That has led us in California and the US in general to instead kind of focus on the supply we can get from potable reuse. So here we see the wastewater that leaves the city going to a wastewater treatment plant. Historically, that treated wastewater has just been discharged to the ocean or to a receiving body. And now what we've been looking at for more than a decade now is advanced water purification, or treating that water to very high quality so that it can be reused for potable purposes. And so you can see the loop here going back from our wastewater back to our supply. So next slide. But with this, we've invested quite a bit in these advanced water purification facilities or potable reuse facilities, and we're depending on a strong supply of treated wastewater. But with this investment and concern for stranded assets, we want to make sure that there's sufficient wastewater supply. So next slide. If in fact that wastewater supply decreases, or there's not enough, if we're trying to do an expansion of the facility, and that could be due to upstream non-potable reuse or other diversions even beyond that. So if we don't have a sufficient wastewater supply, my team has looked at what can we do if we have this facility built with a lot of the same processes as a desalination facility. So next slide, we've looked at if we could bring seawater in, and we've called this concept seawater augmented potable reuse. And it takes advantage of the similar treatment trains. And so we've proposed these concepts to see if there's value in combining and diluting both water supplies. So next slide. This is a series of papers we've worked on. We've had academic contributors as well as practitioners. We've worked with a couple of places in California that are looking at concepts of integration. So next slide. And it's not just seawater augmented potable reuse that we're looking at, it's also wastewater augmented desalination. So that's kind of the left-hand side. So if you have a region, perhaps Middle East region or Australia, that has invested more in their desalination infrastructure and is now looking at, okay, we're doing this desalination while at the same time we're just discharging our treated wastewater. Would it be possible to augment our wastewater, or sorry, our desalination supply with wastewater? And I should note, when we're looking at this slide, right now we do use the treated wastewater to dilute the brine. So our systems are already integrated. The treated wastewater can dilute that desalination brine so that discharge is easier. Also, if you look at kind of right underneath the city, if you're thinking seawater augmented potable reuse is a crazy thing, we are already actually doing it, because in a lot of places, low-lying wastewater treatment plants, their aging, corroded infrastructure into those seawater is flowing in, infiltrating the system, and having to be dealt with the RO process, the reverse osmosis process at the potable reuse facility. So although these seem like new and perhaps shocking, we can't integrate these flows, actually they already are integrated to some extent. So next slide. And there's a big role of chemistry in the viability of these integrations. Like I said, these are concepts that we've proposed and we're analyzing. There's details to be worked out, including a lot of chemistry details on the product water quality. Are we forming disinfection byproducts? Are we getting dilution of contaminants of emerging concern in the wastewater stream? Is that enough? Is dilution enough? Looking at the efficiency of the treatment processes, we need to consider how the organics in the seawater are different than the organics in wastewater, and also the impacts of dissolved salts on the wastewater treatment processes. And for sure, we also need to consider piping at potable reuse facilities. Maybe the selection of stainless steel or other piping needs to be reconsidered if we're blending these streams. And I think that's it. Thank you.
Great. Have everyone back together. So first of all, thank you for all three of our experts who were sharing a unique and yet in a common theme around desalination and membrane tech. So I think we have maybe 1 or 2 minutes left. Any final words or thoughts quickly? 2 minutes, I was just told. If not,
I can just chime in real quick.
Please, David. Yeah.
The technologies we choose should be viewed in contrast to the current options. So in the US, we are just drastically taking away all our groundwater supplies. And so, for instance, the states on the US-Mexico border get the majority of their water from groundwater, fossil water. And we're also emptying entire rivers, right? So the Rio Grande is going empty in a few places. The Colorado River is almost always going empty. And these are ecologically devastating. So we're looking at, yes, there's some drawbacks for these technologies, but compared to the alternatives, we view this as a very sustainable technology for the future.
And a lot of the potable reuse projects were designed or were implemented because there was concern for where the treated wastewater was going to be discharged. And by reusing it, we have this added benefit of additional supply. But a lot of it was in protecting the sensitive environments that we are discharging treated wastewater to. And I think that's important worldwide.
Great. Well, thanks again for the panel.